We'll now start talking about congestion control. You may wonder what we need another mechanism for. As you remember, flow control ensures that the destination never receives more than what it's capable of transmitting. The thing is that somewhere between the sending and receiving endpoints, there might be a router, which routes several connections. They don't see each other, but they use the same resources, and as a result, the queues fill up. Packets might drop, and queue delays may increase. So the moment this event happens, we must resolve it somehow. Because as we know, TCP is a distributed protocol. The next part is how the congestion control is realized within TCP. So let's now look at a case in which congestion occurs and why we need a mechanism in addition to flow control. In this case, we have 4 hosts connected through a router. There are 2 hosts on the left sending information and 2 hosts on the right receiving it. We'll assume the traffic that arrives to the 2 receiving hosts leaves the router on the same link at a bandwidth of R. And the 2 hosts sending information are sending at rate lambda in. Let's assume we have no retransmissions and that the buffer within the router is infinite. In other words, if more packets are arriving than sent, they will be accumulated in the router's queue. It's clear that if hosts sending less than R divided by 2, all the incoming traffic gets sent out and there is no congestion, meaning that the sending rate is precisely the receiving rate of the traffic, in both hosts receiving it. The moment that the sending rate gets close to and surpasses R divided by 2, because each host sends the same traffic, neither of them will receive more than R divided by 2. Because the queue in the router can be of infinite length, the moment that the sending rate comes close to the bandwidth of the outgoing link, you will see that the queuing delay grows. This means we have congestion. And you see that flow control won't help at all in this case. It simply can't deal with this case. For this, we'll need a new mechanism called congestion control. Let's now look at the second case. The difference here from the previous case is that inside the router we have a finite queue, and in the transportation layer we have some timeouts of packets, so the transportation layer will resend them again. So now we'll try to understand what happens in a case where the router queue is limited, and we'll still assume some perfect knowledge about the size of the queue and how high the load is. Because of that, every host sending data will only send data when there is a free space in the queue. Again, this is not realistic because hosts send data into the same queue in a distributed, unsynchronized way. And in this case, you'll see that if lambda in is smaller than R divided by 2, then lambda in is equal to lambda out. And that is exactly what is described in this graph here in the image. We'll slowly get to more realistic models. We remember that in the router we have a finite size queue, so congestion can occur, and we assume that packets can drop, and we'll assume that somehow the hosts sending data know that the packets dropped can be resent, which is a limited kind of retransmissions, meaning that at the transportation layer we have all the data transmitted from the application layer. Additionally, there are all the retransmissions of packets that can drop due to the congestion. So, in what we just described, if each of the hosts is trying to send at a rate of R2, then part of the packets can be retransmitted in the transportation layer. But if we look at it asymptically, the good put is still close to R divided by 2. Think about why this is. We'll now add duplicates to the picture as well, meaning that the packets can drop in the router because of congestion, and we'll assume that because of the timeout, the host sending data can send the packet again. Then more than one copy of the data can arrive at the endpoint. What is the cost of duplicate packets created because of drops while the router queue is congested? We need to transmit more data, including the duplicated packets, which will cause us to work harder and reduce the good put. Let's try to improve our typology. We see that there are currently 4 hosts sending data, and we have paths that include several routers, and we'll also assume that packets can drop because of the timeout and be retransmitted. So if we look at what is happening here now, the moment lambda n increases, then all of the blue packets going through the same router will drop, and as a result, the throughput of the blue packets will actually reach 0. This is the phenomenon. The moment the path between hosts includes several routers, one of them is congested, and because of that, it is dropping packages. We will send the packages another way. This will cause a high use of other routers' capacity, which is wasted for our retransmitted packets. We could have perhaps used that capacity for other packets, which would pass through those routers and not pass through the router that dropped the packets. This is another effect of congestion.